Ladies and gentlemen, today's topic is a very special and interesting group that we will be dealing with a lot in future lessons. Lesson 5 in group theory talks about the symmetric group. But what is a symmetric group and why is it so important to discuss? Well, to answer that question, consider a set of playing cards. Consider 4 playing cards here. And if I make a shuffling of the playing cards, well, I will get the same elements. 1, 2, 3, 4. It's just that the order of the elements is displayed differently. So this action of shuffling is what we call a permutation. A different permutation of the set of playing cards might be this sort of shuffling. So we can have different permutations of the same set of playing cards. What questions can we think about when considering the set of permutations? Well, we can ask ourselves, what happens if we perform one permutation and then we perform another different permutation afterwards? What will that equal? Another question we might ask is, what happens if we perform the same permutation, so the same sort of shuffling over the cards over and over again? What will we get? Will we ever get back the original configuration of cards? 1, 2, 3, 4? Lastly, what would happen if I reverse the permutation that I already did? Is that even possible? So all of these questions can be translated into questions in group theory, and we will find that the notions we have studied throughout the lectures will be very useful in answering these questions. The topics of today's lesson will be covering the 4 topics here: the symmetric group. We will be defining what it is and why, in fact, it is a group. We will be defining what a cycle is, and then we will claim that every permutation can be written as a product of disjoint cycles. This will greatly simplify our calculation. And lastly, we will be mentioning what a conjugation of an element is, and we will be talking about what the order of a permutation is. Let us start with the definition. Let E be a non-empty set, so a set that contains at least one element. We define the set SE by the list of all the permutations that are possible. So a permutation sigma that takes an element from E and sends it to E. So E to E, and sigma is bijective. That means sigma is invertible. There exists an inverse operation that sends it back to where it was before sigma. So now that we have defined this set, later we will define that this set of permutations is in fact a group by proving that it is associative, there is an identity, and there are inverses. But we need to first lay out an example. So for an example would be, if we take E to be a set of 2 elements, I call the elements apple and orange. I don't really care what I call these 2 elements. What I care about the most is in how many ways I can arrange these 2 elements. So SE will give me the elements which in fact rearrange the elements of E. So the first element in SE will send each element to itself. Apple goes to apple and orange goes to orange. The other element will send apple to orange and orange to apple. I call it sigma. In fact, these 2 are the only permutations that are possible on the set E. And these, in fact, ID and sigma, are called permutations. It is important to note that no matter how many elements I have in E, there is always going to be an ID permutation that sends all the elements to themselves. So when we consider the set E, we do not really care about the labeling of the elements so much as the ordering of the elements. So instead of apple and orange, we can just say the numbers 1 and 2 to relabel the elements. So E could be just 1 and 2. So in this case, the set of permutations would contain identity and sigma, where identity sends 1 to 1 and 2 to 2, and sigma sends 1 to 2 and 2 to 1. So more generally, if we have more than two elements, we can say E containing 1, 2, all the way to n. So in this case, we can write the set of permutations of E to be Sn instead of Se, where n denotes the number of elements in E. Let us now prove that Sn, the set, is in fact a group. To do that, I need to define an operation on Sn. If I have two elements in Sn, sigma and tau, so these are two permutations, we can consider their composition rho. What is decomposition, and why is decomposition a valid operation? So here we have that tau is some permutation that, for example, if we take the set 1 to 3, it sends 1 to 2, 2 to 3, and 3 to 1. So this is what tau is defined to be, for example. Later, we define sigma to be 1 to 3, 2 to 2, and 3 to 1. So if we operate on this set 1, 2, 3, if we do tau, tau will send 1 to 2. But then if we perform sigma right after, it will send the resulting 2 to just 2. So if we combine the effects of tau and sigma on the element 1, we can see that 1 is ultimately sent to the element 2. So we can just, instead of sending it in 2 steps, we can send it in 1 step. 1 sent immediately to 2. The same can be said about 2 and 3. Notice that 2 is sent to 3 by tau, and 3 is sent to 1 by sigma. So to summarize the journey of 2, we can say that 2 is sent directly to 1 at the end of the day. And for 3, well, 3 is sent to 1 by tau, and 1 is sent to 3 by sigma. So this is equivalent to saying 3 is just sent back to itself. So this operation gives us another permutation which we call rho. And rho is in fact a permutation which is an element of Sn. So we have just successfully proved, for this example of course, that the operation of composition makes the set Sn into a closed set with respect to this operation. So next, there is the fact that composition is associative. This, I hope, is intuitive enough, and I will leave this to you as an exercise. Next, we will prove that there is an identity permutation. Well, we have just already figured out what the identity permutation is, and we have called it by ID. This is the permutation that sends every element to itself. So in this case, it would send 1 to 1, 2 to 2, and 3 to 3. And if we take the composition of ID and any other permutation, we would find that ID has no effect on the resulting permutation. So ID is in fact the identity permutation. Lastly, we will prove that for any element, sigma, there exists an inverse. And in fact, it is true because we have just said that the set of Sn is all the sigmas, all the permutations that are bijective. So the maps that are bijective have, by definition, an inverse. So for all sigma in Sn, there exists an inverse that is in Sn because sigma is bijective. So by definition, it has an inverse. Hence, the set Sn coupled with the operation of composition of permutations is a group. And now it is time to ask, what is the cardinality of Sn? In other words, how many permutations are in Sn? Well, to answer that question, if we have a set of elements, let's say 1, 2, 3, 4, all the way to n, well, we know that every permutation is completely determined by where it sends each element. So let us start by counting how many ways we can send one element to the other set here. So this set has n elements because a permutation sends E to itself. So it also has n elements. So let us start by seeing where the permutation can send the first element. The first element can be sent over here. That is what the identity can do. But it also can be sent over here. It can be sent over here. It can be sent to n places because we have n positions where it can be sent to. So there are n possibilities, first of all, for the first element. For the second element, if we place, let's say, 1 over here, the second element will have this place, but it will not have this place, not a possibility because it's already occupied by the first element. So it will have n minus 1 possibilities. So for each of these n possibilities of placing the first element, we have n minus 1 possibilities for placing the second element. So we have n times n minus 1 possibilities. What about the third element? Well, we continue this pattern to see that we have n minus 2 possibilities to place the third element. And this continues all the way until we exhaust all of our elements. And this, in fact, is equal to n factorial. So the cardinality of Sn is n factorial. In other words, in a group of 5 elements, there are 5 factorial possible permutations. 120 permutations in a group, in a set of 5 elements. Now that we have proved that the set of permutations of some elements 1 to n is in fact a group, let us use that in an example in our newer section, cycle decomposition. Before we get to cycle decomposition, we will go through the example where we will have a couple of permutations. We will define them explicitly, and then we will see what happens when we compose 2 permutations and what happens when we take the inverse of a permutation. So let sigma be in Sn. Let sigma be a permutation. We can write sigma in this format. So it takes the elements 1 all the way to n, and each element is sent to some other element by sigma. So 1 is sent to sigma of 1, and sigma of 1 could be any number between 1 and n. 2 is sent to, you guessed it, sigma of 2. 3 is sent to sigma of 3. N is sent to sigma of n. So this is how we explicitly mention where sigma sends each element of the set 1 to n. Now, what about the inverse of sigma? The inverse of sigma is the map that sends the images of sigma back to the original element. So it sends sigma of 1 back to 1, and sigma of 2 back to 2, sigma of n back to n. Let us look into an example now to make all this notion very clear. So, for the example, we will consider only 3 elements, 1, 2, 3. And for these 3 elements, we will take some permutations. In fact, we will take 2 permutations, sigma and tau. So we call sigma and tau elements of the group S3. So tau and sigma, we will define them as such. Tau is defined as the permutation that sends 1 to 2, 2 to 3, and 3 to 1. Sigma is defined as the map that sends 1 to 3, 2 to 2, and 3 to 1. Now let us calculate what tau inverse looks like. So tau inverse is also an element of S3 because remember S3 is a group, so any element in the group has an inverse. And tau inverse is calculated as such. So because tau sends 1 to 2, tau inverse will send 2 to 1. So it sends it back to the original number. Because tau sends 2 to 3, tau inverse sends 3 to 2. And because tau sends 3 to 1, tau inverse sends 1 to 3. Let us look into sigma composed with tau now. To do that, we need to always start from the right and then move to the left. So we calculate tau first, and then we calculate sigma on the output of tau. Tau is the map that sends 1 to 2. Sigma is the map that sends 2 to 2. So if we combine these two operations together, we see that sigma sends 1 to 2. Tau sends 1 to 2. And sigma sends 2 to 2. So at the end of the day, the composition of both sends 1 to 2. Let us look into the other elements. We have that tau sends 2 to 3, and sigma sends 3 to 1. So the composition, sigma tau, sends 2 to 1. Let us look into the element 3. Tau sends 3 to 1, and sigma sends 1 to 3. So at the end of the day, 3 only goes back to itself. So these are very useful examples to help us understand how to explicitly describe each permutation and their composition in Sn. Now the example that we've seen takes a little bit of time to explicitly describe where the permutation sends each of its elements. So is there a way to describe the same permutation but in a shorter method? Yes, there is. And now I will be defining what a cycle is so that we can get started on this shorter way. A permutation sigma is called cyclic of order m, or an M cycle if we have a list of elements A1, A2, all the way to AM, such that sigma sends AI, so I for any element I, between A1, between 1 and M minus 1. For any of these A1 to AM minus 1, sigma sends AI to AI plus 1. And sigma sends AM, so the last element on the list, to A1, the first element in the list. And sigma of A is equal to A for all A that is not in the list A1 to AM. So sigma fixes any element A that is not found in this list A1 to AM. In this case, we write sigma equals A1, A2, A3, all the way to AM, and then we close the parentheses. So this gives a complete description of sigma as a permutation if sigma is an M cycle. So what this definition essentially says that sigma is a permutation that sends A1 to A2, it sends A2 to A3, it sends A3 to A4, A4 to A5, and the last element, AM, sigma sends that to A1. And so we call this a cyclic permutation of order M, or an M cycle. We could also write sigma as the permutation A2, A3, all the way to AM, and then A1. And this, in fact, gives the same description for sigma, because we can see that it does not matter the order in which we start. So we can start with A2, but the cycle remains the same. AM is still sent to A1, and A1 is still sent back to A2, and we have the same permutation. So in fact, we can start our M cycle from any element in the cycle. It's just the order of writing the elements has to be the same. Let us look now at an example to make the definition clearer. We have two permutations of S5. We call them sigma and tau, and we define them each in their own way. It is now up to us to write each permutation in the manner in which we discussed earlier. So let us start with tau. How is tau written in a cyclic format? So we start by opening the parentheses, and we pick any of the elements 1 to 5. Let us pick the element 1. I write 1 here, and I say that 1 is sent to 2 by tau. So I'm just going to write 2 over here, because that's where 1 is sent to. Now I'm going to see where 2 is sent to. And 2, in fact, is sent to 3. So I'm going to write 3 here. I repeat, 3 is sent to 4. I write 4 here. And 4 is sent to 1. So instead of writing 1, I'm going to just close my parenthesis. But why is that? Well, remember in the definition, the cycle will send the last element to the first element. And since 4 sends to 1, that is exactly what we're describing here. The permutation sends 4 to 1. So 1 sends to 2, 2 sends to 3, 3 sends to 4, and 4 sends all the way back to 1. And we close the parenthesis. And 5, well, 5 is sent to 5. So tau essentially does not change 5. And we've seen that 5 does not belong on the list, which agrees with our definition. So this, in fact, completes our description of tau as a 4 cycle. So it is, in fact, a cyclic group. Whoop. The camera does not want to stay still. So we have a 4 cycle here, or a cyclic group of order 4. So what about sigma? Well, sigma sends 1 to 5. So we start our cycle 1 going to 5, and then we see where 5 is sent to. Well, 5 by sigma is sent to 2. So we just write 2 here. Now we see where 2 is sent to. 2 is sent to 3 by sigma. So we write 3. And we see where 3 is sent to. 3 is sent to 4. And 4 is sent to 1. So 4 is sent all the way back to the first element. We close the parenthesis. This, in fact, covers all of the elements of 1 to 5. So this is a 5 cycle, a cyclic permutation of order 5. Now, not only does this save time computing sigma and tau, but we will see that the definition will save us time in computing the composition of sigma and tau as well. So let us do that. Let us calculate the composition using these cycles. So tau composed with sigma equals, we write tau 1, 2, 3, 4, and we write sigma afterwards, 1, 5, 2, 3, 4. The resulting permutation will look like this. So we open our parentheses, we start with the right, and we see where the element is sent to, and then we go to the left and we see where the output of the first cycle is sent to. So the first step is to start by any number on the right. I will say we start with 1. So I will start with 1 here. 1 is sent to 5. So I will see where 5 is being sent to on the left here. I see that 5 does not belong in this list, so 5 is fixed over here. So 5 is being sent to 5. So essentially, 1 is only sent to 5, and nothing happens afterwards. So we just write 5. Now we want to see where 5 is being sent to. So to do that, we go back here, and we start with the right, and we see where 5 is being sent to by this cycle. So the 5 cycle here sends 5 to 2, and we see where 2 is being sent to on the left. 2 is being sent to 3. So at the end of the day, we're sending 5 to 3. Let us now see where 3 is being sent to, because we're here. We want to see what's the next element in our list. So we start on the right. 3 is sent to 4. And let's see where 4 is on the list. It's over here. And we know it's sent all the way back to 1. So the result is just 1. So instead of writing 1, remember, we close the parentheses. We close the parentheses, and we see that 3 is sent back to 1. So this is one cycle that we have, but are we done? No, we have not covered all of the elements. Let's see what happens to 2 and 4. So what happens to 2 and 4 here? Let us see. So we open another cycle, and we start with the element 2. So what happens to 2 is sent to 3, and 3 is sent to 4. So resulting says that 2 is sent to 4. Now what happens to the element 4? Well, we see that 4 is sent to 1, and 1 is sent to 2. So that means 4 is sent to 2. But we do not write 2 here because 2 is already written. All what we do, again, we close the parentheses and we send it back to the first element in the cycle. So this completes the description of the composition tau sigma. So here we have a 3 cycle and a 2 cycle describing this permutation. So 1 is sent to 5, 5 is sent to 3, 3 is sent to 1, and 2 is sent to 4, and 4 is sent to 2. So if we write this explicitly, we would say that 1 is sent to 5, 5 is sent to 3, 3 is sent to 1, 2 is sent to 4, and 4 is sent to 2. And that is how we quickly compute the permutations and their compositions by just using cycles. Now that we have introduced cycles, I will be going into what a disjoint cycle is, and then I'll be explaining why it is important to decompose our permutation into disjoint cycles. So, starting with the definition of a disjoint cycles, we say that two cycles A1 to AK and B1 to BL are disjoint if AI is not equal to BJ for all I and j. So an example of this would be the composition that we have in fact saw earlier. So tau and sigma are equal to 153 to 4. So these two cycles share no elements in common, and that is why we call these two cycles disjoint. So 153 is a cycle that is disjoint from 2, 4. And the advantage of having disjoint cycle is that disjoint cycles are commutative. So if sigma and tau are disjoint cycles, what this means is that sigma tau is equal to tau sigma. So essentially saying that 153, 2 and 4 is equal to 2, 4, 1, 5, 3. And we will see that this greatly simplifies our calculation later on. The proof of this proposition I will leave to a later video in my YouTube series. But now I will move on to an example of the disjoint cycles of a permutation. So let sigma be a permutation of S9. So we have 9 elements in our set, and we have a permutation that permutes these 9 elements. Sigma here is described to be 2 going to 4, 4 going to 5, 5 is sent to 8, and 8 is sent to 2. 6 is sent to 5, 5 is sent to 1, 1 is sent to 6. 3 is sent to 5, 5 is sent to 8, and 8 is sent to 3. This completely describes sigma for us. We notice that these two cycles here are not disjoint because they share the element 5. So the proposition tells us that we can rewrite sigma so that sigma is written as a composition of pairwise disjoint cycles. So let us do that. In fact, let us write the pairwise disjoint cycle decomposition of sigma. So let us start. Sigma sends, we will start by treating sigma as different, a composition of 3 different cycles, a 4 cycle, a 3 cycle, and a 3 cycle. So we have here that 3 is sent to 5, and 5 is sent to 1, and 1 is sent nowhere. So in fact, 3 is sent to 1. Now let us see where 1 is being sent to. We have that 1 is sent nowhere here, and 1 is sent to 6, and 6 is sent nowhere. So in fact, 1 is only being sent to 6. Lastly, or maybe not lastly, why did I say lastly? Anyways, we have 6 is sent to nowhere, so it just remains 6 for the moment. But if we look to the left, we have 6 is sent to 5. And if you look to the left, we see that 5 is sent to 8. So 6, in fact, at the end of the day is sent to 8. And we see where 8 is being sent to. So 8 is being sent to 3. And we look here, we see that 3 is sent nowhere, so it just remains 3. And we see here that 3 is also sent nowhere, so it just remains as 3. But we don't write 3, remember, we already have 1 here. So we just close the parentheses and we have our first cycle. So our first cycle contains 3, 1, 6, 8. So we still have 2, 4, 5, and 7 to worry about. So let us do that. Let us see where 2 is being sent to. So we have here that 2 is being sent nowhere, 2 is being sent nowhere, and 2 is being sent to 4. So we say that 2 is being sent to 4. Let us see where 4 is being sent to. Nowhere, nowhere, and 4 is sent to 5. So we just write 5 over here, and we see that 5 is being sent to 8. And here we see that 8 is being sent nowhere, so it's just 8 for the moment. We go to the left and we see that 8 is being sent back to 2. So instead of writing 2, notice there is already a 2 here. So we just close our parentheses and we say 5 is being sent back to 2. So now we've covered more elements. We just have 7, which is remaining. And we see that 7 is in fact not in this list, not in this list, and not in this list. So in fact, sigma sends 7 to 7. 7 goes nowhere. So we do not write 7 over here. And that will be enough to describe all of the permutation sigma. And we notice here that these two cycles, 3168 and 245, are in fact disjoint cycles. So now we have the advantage to write them as 245, 3168. This is the commutative property of disjoint cycles. Now you might ask, what is the use of this commutative property? And that will come later on. Now that we have defined what the notion of disjoint cycles are, we will be using it to further our study of permutations. We will go into conjugation and the order of a permutation. Let us start with the definition of a conjugate. Let sigma and tau be permutations in SE, sigma being the permutation x1 going to x2, going to x3, going to xm, which goes back to x1, be an M cycle. The conjugate of sigma with tau, another permutation, is tau sigma tau inverse. So it is the composition tau with sigma with tau inverse. So basically you apply the composition, you apply tau inverse, then you apply sigma, then you apply tau. So this conjugate, in fact, is easy to calculate. You do not have to calculate it explicitly, and because that would take some time. In fact, the next proposition tells us that tau sigma tau inverse is in fact tau x1, tau x2, tau x3, all the way to tau xm. So you just simply take the element x1 from sigma and you apply tau on that element and you get tau x1. And you continue this process with all the elements in the cycle sigma. The proof of this proposition will also be in a later video that I'll be posting very soon on the series. But for now, let us see an example where this proposition can come in handy. So if sigma and tau are permutations in S6, so we have 6 elements and these are permutations, we have sigma, which is 164, and tau is 12453, then if we will calculate sigma tau sigma inverse in 2 ways. The first way is explicitly, the second way is using the proposition. And you will see for yourself which is the faster way. The first way is to just write down tau sigma and tau inverse. Well, tau inverse, we need to know how to write the inverse of a cycle. So we will write the inverse of this and the inverse of that. So the inverse of 1, 2 is going to be the inverse of 1, 2 is going to be 1, 2. Well, technically, we have to write 2, 1. We reverse the order, but we already said that it doesn't matter if we start with 2 or if we start with 1. So we could just say 1, 2, but I'll just leave it like that. Now, what about 453? Well, the inverse of 453 is equal to 354. So all what I did is I reversed the order in which the elements are written in the cycle. you can check for yourself that 453 composed with its inverse is equal to the identity. So in fact, it fixes every element. And that I leave to you as an exercise. Anyways, we have our composition here, and it's time to get in the calculation. We have that the element 3 is sent, so let me use a laser here. So 3 is sent to 5, and 5 is sent nowhere here, nowhere there, and here 5 is sent to 3. So 3 is in fact sent to itself, and we do not write 3 in the cycle because it is fixed. What about if we start with 5? So let us start with 5. And we say that 5 is sent to 4, and 4 is sent nowhere here, 4 goes to 1, and 1 goes to 2. So 5 goes to 2. And where is 2 being sent to right now? We see that 2 is sent nowhere here, 2 is being sent to 1, 1 is being sent to 6, and 6 is being sent nowhere on the left. So in fact, we end up with 6. What about if we start with 6 now? We see that 6 is sent nowhere over here. We start here, 6 goes to 4, and 4 goes to 5. So 6 goes to 5, but remember we already wrote that, so we can just close our parentheses. So we've said that 3 is fixed, 5, 2, and 6 are already covered. Let's see what happens to 1. So this 1 is not being sent anywhere here. 1 is sent to 2. 2 is not being sent anywhere here, neither here. And lastly, 2 is being sent back to 1. So we write that 1 is sent to 1. It is fixed, so we do not write it in our cycle decomposition. So in fact, the tau sigma tau inverse is equal to 5 to 6. Let us now use the proposition to calculate this conjugate. So to calculate this conjugate, simply notice that the elements 1, 6, 4, we need to see where tau sends each element. So tau sends the element 1 to 2 by definition of tau, because tau sends 1 to 2. So instead of writing 1, we're just going to write 2. What about 6? Well, let us look here. Does tau send 6 anywhere? No. Tau fixes 6. So in place of 6, we're going to write 6, because 6 is fixed by tau. What about 4? Let's see what tau does with 4. Tau sends 4 to 5. So instead of 4, we write 5. And we close the parentheses because that's all the elements replaced in sigma. So in fact, we see that these two are the same. Well, you might ask, wait, this is 526 and that's 265. Yeah, they're different technically, but they're in fact the same permutation, because remember, we do not care which number we start with as long as the order of the numbers left to right are the same. So we can start this by saying, oh, we start at 5, and then we write 2, and then we write 6. 5, 2, 6. And now we see that it's in fact the same permutation exactly. The last order of business to discuss is, well, no pun intended, because that is in fact what we're discussing. It's the order of a permutation. So we will find that the disjoint cycles idea that we discovered is a very useful idea in calculating the order of a permutation. So let sigma be some permutation in Sn. The proposition tells us that the order of sigma is just the least common multiple of the lengths of the cycles in its composition. But to calculate the least common multiple of the lengths of the cycles, we need to calculate first, practically, the order of a single M cycle. So let sigma be an M cycle. Let us say sigma is, let's say, 1 goes to 2, which goes to 4. Okay? So we want to calculate the order of this element of the group. Recall that an order of an element is the smallest integer, such that if you take that element to the power of the integer, you will get back the identity element. The identity element of the group of permutations is the permutation that fixes all of the elements. In other words, it's the permutation that contains no elements in any of its cycles. Here clearly sigma is not the identity because it sends 1 somewhere else, not back to 1. So we want to really send 1 back to 1. How we do that? So if we take sigma squared, right? So sigma squared is 1, 2, 4, 1, 2, 4, and we calculate that normally. We have that 1 goes to 2 and 2 goes to 4. So 1 goes to 4. Now let's see what happens with 4. 4 goes back to 1 and 1 goes to 2. So 4 goes to 2. And lastly, we have that 2 goes to 4 and 4 goes to 1, completing the cycle. So sigma squared gives us 1, 4, 2. That is clearly not the identity. So we need to go with a larger power of sigma. So let's say sigma cubed. So sigma cubed is sigma squared times sigma, right? And sigma squared is already calculated to be 1, 4, 2. And sigma is 1, 2, 4. So that is equal to, again, 1 goes to 2, 2 goes to 1. So 1 is fixed. So 1 is fixed, 1 is not in any cycle. Let us see what happens to the element 2. So 2 goes to 4 and 4 goes to 2. 2 is fixed as well. Okay, what about 4? 4 goes to 1 and 1 goes to 4. 4 is also fixed. So all 3 elements are fixed. And of course 3, the element 3 is nowhere to be found. So that's automatically fixed. So all the elements are fixed and sigma to the 3 is the identity permutation. So in fact, 3 is the order of sigma, which we denote by this symbol here. So the order is equal to 3. So what is happening here? Why is the order is equal to 3? Is it because sigma is a 3 cycle? The answer is yes. Absolutely, it is because of that. Because notice that sigma sends 1 to 2. Sigma squared sends 1 to 4. Sigma to the 3rd power sends 1 to itself. So with each power of sigma, we are increasing the number of steps that 1 jumps to. Okay? So it takes how many steps so that it jumps back to itself? It takes exactly 3 steps. Well, it can also take 6 steps because you can just do that again. 1, 2, 3, 4, 5, 6. We can take 9 steps. So we can take any multiple of 3 steps. But that is also the definition of what an order is. An order, by definition, divides any number that if you take sigma to that power, it gives you the identity. But anyways, that is how we know what is the order of an M cycle. And now this proposition tells us that no matter what permutation we have that the order of the permutation is the least common multiple of the lengths of the cycles in its composition. So let us take an example here. As always, the proof will also be in a future video in this video series. In fact, it will be the next few videos. These videos will cover the proofs of the propositions I've outlined in this lecture. So we have in the example, sigma is defined by the permutation that sends these elements. So what is the order of sigma? We will use the proposition to say that the order of sigma is in fact the least common multiple of the length. So the length of this cycle is 5. This is a 5 cycle. This is a 2 cycle. This is a 3 cycle. And this is lastly a 2 cycle. So the order is the least common multiple of 5 and 2 and 3 and 2. And the least common multiple of all these numbers is equal to 30. Now, sigma to the 200th power is equal to what? Well, obviously, if we do not have the properties that we've discussed, if we do not have disjoint cycles, commutativity, and all of that good stuff, it would take us ages to calculate sigma to the 200th power. But thanks to all these properties, we can calculate it much, much quicker. So sigma to the 200 is equal to all of that to the 200 by definition of sigma. I just replaced the definition of sigma in my formula. And now because it's disjoint cycles, these are all this pairwise disjoint. Because of that property, we can commute all of these individual cycles together until we have 200 of these guys on the left. So we put all 200 of these guys on the left. And then next we put all 200 of these guys here. And then we put all 200 powers of this cycle. And then lastly, we put all 200 powers of this cycle. So if this was hard to understand, remember that if we have commutativity, then the nice thing about it is that if we have, let's say, a times b times c to the third power, let's say, this would be equal to a, b, c, a, b, c, a, b, c, like that. And we cannot really have the next step if we don't have commutativity, which is just to group all the a's together, group all the b's together, and group all the c's together to have this nice compact formula. So commutativity helps us a lot here. And what follows is that we want to write 200 in terms that we can have like a very nice simplification. So we can see that this is a 5 cycle. So the order of this element here is 5. And we just said that if 5 divides the power, that means this gives us the identity. So this is in fact all equal to the identity element. Okay, so that is already very greatly simplified. That's just the identity. Now this is a 2 cycle, and 2 is the order of this element, and 200, the power, is divisible by 2. So that's also the identity. This is also the identity as well by the same argument. Just that this is not quite the same because this is an order of 3, and 200 is not divisible by 3. So what do we do here? Well, the problem already simplifies. Let's rewrite it to just this. So we only have this to worry about. All the others are the identity. And if we multiply the identity with anything else, it's like doing nothing. So we just have 5, 7, 11, all to the power 200. So what can we do to simplify this? Well, we're going to use the division algorithm to put 200 in terms of something times 3, because remember 3 is the order of this, plus a remainder. So 200 divided by 3 is equal to what, first of all? So 200 by 3. 3 times 6 is 18, minus is equal to 2. 3 times 6 is 18, minus is equal to 2. So 200 is equal to 3 times 66 plus 2. So we rewrite 200 in this form. 5, 11, 7. 3 times 66 plus 2. And we say this is equal to 5, 11, 7. 3 times 66 times 5, 11, 7 squared. And now we find that this guy here is reduced to the identity. Why? Because we can just say this is equal to 5, 11, 7 to the third power to the 66th power times 5, 11, 7 to the second power. And this guy here is the identity because 3 is the order of this 3 cycle. So this is equal to the identity to the order 66, which is equal to the identity, times 5, 11, 7 squared. And notice that 5, 11, 7 squared is equal to 5, 11, 7 times 5, 11, 7. And that is very, very easy to compute. We see that 5 is sent to 11 and 11 is sent to 7. So 5 is sent to 7. 7 is sent to 5. 5 is sent to 11. So 7 is sent to 11. And lastly, 11 is sent to 7, which is sent to 5. So we just close our parentheses, giving us sigma to the 200th power. So easily with the properties of commutativity, disjoint cycles, and the order of an element. And this is the magic of group theory. And we have only scratched the surface when it comes to these powerful computations. And with this, we complete the last point in this lecture. And I will be seeing you next time. If you like this video and if you're liking this series, please like and subscribe and share with anybody who would be interested in this very, very fascinating subject.